So in the last section, it's just the case just go away from the Hermitian operator and to make it slightly more general. But if we're too general, then there's nothing we can do. And so the slightly more general is the operator that is not Hermitian. So it means the operator A is not the same as a join. So this is called the normal matrix. The definition of this normal matrix is start from here. So it's the A dagger is not equals to A, but then I mean, it can include the case because the definition is the A dagger is commutative with A, right? So that's called normal matrix. Obviously, if A dagger equals to A, this is true. So that include that. So that include Hermitian matrix. Hermitian matrix is A dagger is A, right? So that obviously satisfies that. And then the unitary matrix also satisfies that because unitary matrix A dagger is inverse, right? A inverse, and A inverse is commute with A, obviously, because you have A inverse. A inverse includes the identity matrix, but you know that, right? So this is just the usual matrix property, and so it's include the Hermitian matrix satisfy that unitary matrix. Also, the anti-Hermitian also satisfy the obviously. Anti-Hermitian is just you have a negative sign too. But then obviously would be more general than all these. There are cases that not including all this, and the only the property that carry on from the Hermitian matrix is that the A dagger and A will have the common eigenvector, which is a general case. If you have A and B, you have two operators commute, then A and B operator will have the common eigenvector. You learn about that, right? Yeah. So like in quantum mechanics, you learn about that, and the only thing that is more general than any other operator commute with A is that the eigenvalue is the complex conjugate of A dagger is the complex conjugate of A. Okay, so that we can show that in a quite straightforward way. And the textbook, I will deviate from the textbook. The textbook use this Dirac notation, the bracket notation, which is I found it a little confusing. So I will not use that. But to show that actually quite easy. To show that they have common eigenvector is quite straightforward. Say, you just assume like A operate on a certain function phi. You can have an index, but you don't need the index. Just one function, one eigenfunction is lambda phi. Right? Then you operate on. You consider A like A dagger. A dagger. The two way to do that, either way is fine. A dagger or A dagger. Consider A dagger and phi, right? A dagger and phi, and using the fact that they commute is A dagger A phi, and then using this is lambda phi. This is lambda phi and A deck. Right. So then just compare this with that. You can say this is now a vector. This is a vector. A operator on this vector give you the same vector with the same eigenvalue. Okay, so it means that the A dagger phi is also. It depends on the two. There's two cases. One is all the eigenvalues are non-degenerate. So you have each one eigenvalue for one eigenfunction. That would be the easiest way to argue. But even with the degeneracy, the argument is just basically the same. It's because they have all the same eigenvalue. So you just write it down with an extra argument for the degenerate case. But for non-degenerate case, obviously, because A phi is lambda phi and A operator on this vector is this vector, it means that A vector phi must be proportional to phi, because this is already an eigenvector. This is the same eigenvector for non-degenerate case, but up to a proportionality constant. So it's proportional to phi, must be proportional to phi. Say a proportionality constant is the Z phi, right? And this itself is like an eigenvalue equation. So A deck operator on phi is this function, this as a proportionality constant and times phi, right? So it means that they have the same compare this with that. So A and A deck have the same eigenfunction, not necessarily the same eigenvector. Eigenvalue may not be the same. Eigenvector is the same. Okay, is that okay? So that's very, very easy to see. The next property is the relationship between this C and lambda. All you need to do is like do a scalar product with this one, the phi and this one, right? So like the scalar product phi A phi, right? And then plug that in. This would be lambda phi. And assuming they are normalized, phi is normalized, and it's just lambda. Right? That's straightforward. And now you do the same thing as not the same thing, but you apply the definition of the adjoint operator. So this one is just what we did before is A deck y A. That's just the property of adjoint. We define adjoint operator this way. And now using this equation, A deck phi is conceived. This C is it's just a number, phi, right? And then you use the property of the scalar product. This constant, when you pull that out of the scalar product, this becomes a complex conjugate because it's on the left-hand side. So this is complex conjugate. It means that the C is this lambda complex conjugate. Okay, so that's pretty straightforward. You don't have to follow the textbook using this bracket notation. I mean the direct notation. Sometimes I think they are just abusive of notation, but I don't like that much. Anyway, it's sometimes useful. Like the next section, I can follow the textbook, which is or mostly follow it, not necessarily strictly. Okay, so we show that they have the same eigenvalue value. You can say that they have the same set of eigenvectors. They don't have the same eigenvalue. The eigenvalues have a convex conjugate. All right, so that's the first part. The second part is to show that if you have a set of eigenvalues, they can form an orthonormal set.